Hello everyone, I hope you're all doing well. We're going to be looking at particle kinematics in the radial transverse coordinate system, or what is called as the polar coordinate frame. Okay, so motion in the radial transverse system, or what is also called as the polar coordinates. All right. So what we're going to do first is we're going to be defining what is meant by the radial unit vector and what is meant by the unit vector in the transverse direction. So first of all, some notations. Okay, so I'm going to have ER is the unit vector in the radial direction, and E theta is the unit vector in the transverse direction. Okay, and I'm going to consider a particle on an arbitrary path, and this is viewed by a stationary observer. Okay, so let me first draw the stationary observer right here, and so let's say that this is my x-axis and y-axis. It's not necessary at this point to specify what is x and what is y, but we typically say the horizontal is x and the vertical is y. Okay, so this is the x and the y coordinate frame. This is a fixed observer. Okay, so this is a fixed observer, and this fixed observer is watching the motion of a particle. Okay, let's say that the motion of the particle is in the following direction, going from here all the way on to here. Okay, now I'm going to consider two time instants for this particle. So this is the arbitrary path of the particle. Okay, so this is the path of a particle. Okay, and I'm going to consider, two time instances. I'm going to draw the positions from the fixed observer O to, let's say, a time here where the particle is sitting at that point. Okay, and then after maybe a time dt, the particle is probably moved somewhere here. Okay, and so this is going to be, let's first label the position vector. So this is going to be the position vector r at time t, and then this is the position vector of the particle r at time t plus dt, and in that particular time this particle has traveled by an angle d theta as it traverses this distance ds between the two instances in time. Okay, so this is going to be particle p at t, and this is going to be the position of the particle p at t plus dt. Okay, and let me take this and scoot this down here. All right, so how do I define the radial unit vector? Here is how I define the radial unit vector. Okay, the radial unit vector is always pointing along the direction of the position vector from a fixed observer, okay, and towards the particle, which means that the radial unit vector at this location is going to be pointed out here along the same direction as the position vector. So this is going to be at the radial unit vector at this location here. This is going to be the direction of the radial unit vector. Of course, these are all unit vectors, so they have a magnitude of 1. Okay, so this I'm going to call as E suffix r. Okay, this is at time t, and I'm going to call this as E suffix r prime. Okay, this is at time t plus dt. Okay, and if I have to find out, okay, what is the direction of the transverse unit vector, the transverse unit vector is going to be perpendicular to the radial unit vector. That is the first thing. And then the other thing is the transverse unit vector is going to be pointing in the direction of increasing theta. Okay, which means that, let's say that this was initially where the particle started along this path. Okay, and the transverse unit vector is going to be perpendicular to the radial unit vector, and it's going to be pointing in the direction of increasing theta. Okay, so in this case this is going to be E theta prime. Okay, this is 90 degrees with respect to each other. I'm going to take this P of t plus dt, move that creature a little here, and then draw my transverse unit vector here. Okay, first of all, and let me, sometimes these things get a little unwieldy to draw. Okay, so this is going to be E at theta. Okay, and this is also at an angle of 90 degrees with respect to the ER direction. Okay, so then I'll bring back my P of t plus dt and say, okay, that's where the particle is at that point in time. Okay, and here was P of t. All right. So once we have these directions nailed down, here is what I'm going to be writing out. Okay, so the direction of ER will be pointing towards the particle from a fixed observer in the direction of the position vector. At that time. Okay, all right, so this is the direction of ER, and likewise we want to write the direction of E theta. Okay, direction of E theta. Okay, this is perpendicular to ER, on the same plane as ER, and will be pointing in the direction of increasing angle. In the direction of increasing angle. Okay, so this is the direction of E theta. All right, fantastic. So what are we going to do with all these things? This is typically how we have tackled the normal tangential system. We are going to be writing each of the kinematic quantities in terms of these radial and transverse vectors. Okay, so we're going to be writing the position vector, the velocity, and the acceleration in terms of the radial transverse unit vectors. Let me redraw my figure once again. Okay, so our aim, let me state our aim here, is to express the position, velocity, and the acceleration vector in terms of ER and E theta. Okay, so this is going to be the aim for us, and towards that I'm going to be redrawing my coordinate frame, and then look at two arbitrary time instants like we have done in the past. Okay, so here is the particle. So let's say that this is the path of the particle watched by a fixed observer here, okay, from the point O. Now I'm going to draw an exaggerated viewpoint, of course. Okay, so from here I'm going to draw a position vector to some point in time t here. Okay, so let's say that this is some point in time t, and then maybe there is another point in time t which is sitting somewhere here infinitesimally close to each other. Okay, so I'm going to have unit vectors which I'm going to be drawing in my color frame here. Okay, so this is going to be, first of all, the unit vector in the direction of ER. Okay, kind of hard to snap this in, but I hope that makes sense. Okay, this is approximately in that particular direction, and I'm going to have an e theta which is perpendicular to that. Okay, and you can see that the e theta direction is not necessarily the same as the tangential direction. It is not the same as the tangential direction unless the path is a circular path. Okay, so this I'm going to call as ER and then E theta. Okay, then likewise I'm going to have one more set here. So this is going to be ER prime. Okay, this is a time t plus dt, and you can see that, okay, here is E theta prime. Okay, so this is ER prime, E theta prime. Okay, and then this is the position at time t. This is P at time t, and this is the position at t plus dt. Okay, and likewise this angle here is going to be the angle d theta. Okay, and so let's write this down. So ER and E theta are unit vectors at time t. Okay, and then ER prime and E theta prime are unit vectors at time t plus dt. It should be quite obvious that the direction of the unit vectors are changing, which means that the time derivative of these unit vectors is non-zero. Okay, so since the directions are changing, of ER, E theta, etc. are changing with time, we realize that DER by dt is not zero and dE theta by dt is also not zero. Okay, and of course the other key thing is that these are all unit vectors, so their magnitudes are equal to 1, and likewise here. Okay, they're of unit magnitude. All right, so I'm right at this position here. I'm going to call this as the position vector r of t. Okay, so starting from here all the way up to where that is my position vector r of t. Okay, and I'm going to say that the magnitude of this position vector is little r. Okay, so I'm going to say that, okay, the magnitude of position vector r of t, okay, is going to be r. So this is the magnitude of the position vector at time t. All right, so that's also an important piece of information. So let me start off by writing the position vector. So that should be fairly straightforward, right? Because any vector is its magnitude times its unit vector. So position vector r is nothing but its magnitude, little r, times its unit vector er. Okay, so that is the first thing. So first thing is position vector. Okay, so here I can say that r of t is the magnitude times er. Okay, where r is the magnitude of the position vector at time t. This can be changing with time, which means that r can be a function of time. Okay, unless you are on a path with a fixed radius. If the radius of curvature is changing, then location from a fixed observer is also going to be changing at every point in time. Okay, so this is the expression for the position vector in the radial transverse coordinate frame. Now let us next do the velocity vector. Okay, before I do the velocity vector, here is what I'm going to be doing. I'm going to take this ER and E theta and then ER prime and E theta prime, and I'm going to pin them together. Okay, so let me try doing that. Let me copy these creatures and then let me bring them down here. Okay, probably a better idea is to just draw it myself. All right, that looks a little too small for me to manage. So this is going to be the velocity vector. Okay, that's what we're going to be doing next. But before I do that, I'm going to pin them together by the tail. So the pin the ER, E theta, and the ER prime, E theta prime, unit vectors together. Okay, here is what I'll end up getting. So let me call this as the ER and the E theta. Okay, just an exaggerated sense, and then I'm going to have an ER prime, and then I'm going to have an E theta prime. Okay, so let me write out this one here. These are all unit vectors, so they have a certain direction that they point towards, and their magnitude is equal to 1. So this is ER prime, then I have this as E theta, and so this is going to be E theta prime. And you know from looking at normal tangential coordinates that if I join these two heads together here, then I'm going to be getting DER. Okay, so this is going to be DER. Likewise, if I join these two heads together here, I'm going to be getting DE theta. Okay, and I also know further that the angle inside here is D theta. Okay, and the angle here is also D theta. Okay, this is because that is the same angle that is traversed by the particle as it goes from one point to the other. Okay, over time interval dt. So when you look at these things, it can be proved, okay, which we have done for the normal tangential system. So similar to the normal tangential system, it can be proved that DER is perpendicular to ER and DE theta is perpendicular to E theta. Okay, this is similar to the normal tangential coordinate system. Okay, where we took one of the unit vectors and then we did the dot product, and then we did the time derivative, and then we proved, okay, these are at right angles to each other. Okay, also by construction it can be seen, by construction it can be seen that, look at DER. DER is perpendicular to ER, so it's actually pointing in the direction of E theta. Okay, in the direction of positive E theta. Okay, DER, which is perpendicular to ER, is pointing in the direction E theta. Okay, this you can see from the figure here. Okay, and then likewise DE theta, that's a crucial thing here, DE theta, which is perpendicular to E theta, is pointing in the direction negative ER. So this is positive E theta, this is negative ER. Please look at the figure here once again. Look at dE theta. dE theta is perpendicular to E theta and it's pointing in the direction opposite to ER. Okay, that is the key thing in this particular situation. I want to underline some of these things. So also by construction, okay, we can find out the DER is perpendicular to ER and is pointing in the direction of positive E theta. Okay, likewise dE theta, which we say is perpendicular to E theta, right, is pointing in the direction of negative ER. Okay, and so here is what I can do. All right, so from here I can say that first of all the magnitudes, okay, the magnitude of DER is the magnitude of ER times d theta is also the same as the magnitude of DER prime times d theta, which means that the magnitude of DER is equal to d theta. Okay, likewise the magnitude of dE theta is E theta times d theta or E theta prime times d theta, which implies that the magnitude of dE theta is equal to d theta as well. Okay, so that's an important point that you want to underline here. Okay, so these are all the magnitudes. Likewise, this is the magnitude. I know the magnitude, I know the direction, so here is what I'm going to do. Okay, so based on this, okay, so this is my next point. Okay, so we have, and this is all even before starting to find the velocity vector, and you'll see that once I do this, then finding the velocity vector is not a huge deal. Okay, so we have DER is equal to d theta in the E theta direction and dE theta is equal to minus d theta times ER. Okay, and how did we get this? We got this by saying that, okay, DER is equal to magnitude of DER times its direction, okay, which is going to give me DER is equal to the magnitude times the direction of DER, which is d theta. Okay, so this is how we obtained it. And so this is also something very important. So I'm going to box these couple of things. Let me maybe scoot this guy a little down. Okay, this is something that you're going to keep looking at again and again, even when we hit rigid bodies. Okay, we're going to be looking at these things again and again. And so in rigid bodies, what you'll see is you'll call these as a form of a system of unit vectors which form a triad. A triad is something that is having two unit vectors on the same plane, and then a third one is going to be out of plane. In our situation, the triad is actually going to be the third vector of the triad is actually going to be the z direction. Okay, because we're doing only two-dimensional motion. Okay, all right, so this is what we have. So now I look at the velocity vector. Okay, so back to velocity vector. Okay, I know by definition v is dr by dt. Okay, which means that I can say, okay, v is d by dt of r times er. Okay, this is by means of the product rule, dr by dt er plus r times der by dt. Okay, we shall use the dot notation to denote time derivatives. Okay, so keep this in mind. Whenever you see a single dot, then we have a single derivative with respect to time. Two dots imply two derivatives with respect to time. So you can obviously see here that, okay, v is going to be r dot ER plus R times dER by dt is going to be d theta by dt in the E theta direction, because dER we just did a substitution for dER. Okay, and so this can be written further as V is equal to R dot ER plus R times theta dot E theta, and this can be called as VR ER V theta E theta. This is a fantastic expression. This is something that will be very, very useful when we start solving problems. Okay, and then here VR, which is R dot, is called as the radial component of the velocity. Velocity vector. And V theta, which is R times theta dot, is called as the transverse component of the velocity vector. All right, and that's about it for the velocity vector. We are done. Now we go to the acceleration vector. Okay. If I go to the acceleration vector, here is what I have. Okay, by definition, we have acceleration is equal to dv by dt. Okay, which means that acceleration is equal to d by dt of the entire velocity vector, which is r dot er, and then r theta dot e theta. Okay, now I have a big task in front of me. I have to do product rule many times, and that's essentially what I'm going to be doing. Okay, so I'm going to get, okay, acceleration is now, and I'm going to do the time derivatives very quickly, so I'm not going to be doing a d by dt and so on. So I'm just going to say, okay, this is going to be r double dot er product rule, and then r dot der by dt. Just for that, I'll make use of the d by dt. Okay, then this is going to be the next time derivatives. I'm going to have three pieces in it: r dot theta dot e theta, differentiation of r, differentiation of theta with respect to time one more time, so that's theta double dot, and then lastly I'm going to have r theta dot de theta by dt. Okay, and maybe let me just say, okay, this one corresponds to the entirety of that. Okay, and then likewise this one corresponds to the entirety of the time derivatives for all of that. Okay, all right, so now I'm going to start simplifying. Okay, so this tells me, okay, hey, acceleration is r double dot er, and then r dot der by dt is d theta by dt times in the e theta direction. Then I'm going to have r dot theta dot e theta, r theta double dot e theta, and then r theta dot times minus d theta by dt in the er direction. Okay, and so I'm going to start utilizing common terms here. So acceleration A is one more step, r double dot er, r dot theta dot e theta, because d theta by dt. Then I have an r dot theta dot e theta once again, and then I have an r theta double dot e theta. Then I have a minus r theta dot square in the er direction. Okay, because this is d theta by dt, I have a theta dot, negative sign, so theta dot square. Combine all the common terms. Acceleration is going to be the following big guy: r double dot minus r theta dot square in the er plus 2 r dot theta dot r theta double dot e theta. Okay, and this can be written in the form AR ER plus A theta E theta. Okay, this is first of all the acceleration vector here, this huge thing. Okay, and if I compare it with the general x-verse vector form of writing it, then I can see that, okay, AR, which is R double dot minus R theta dot square, is called the radial component of acceleration vector, and A theta, which is 2 R dot theta dot R theta double dot, is called as the transverse component of acceleration vector. All right, fantastic. I hope the lecture is useful. I'll be giving a very short summary of all of these different coordinate frames in my next concept talk. Thank you very much. Bye bye.